This is the fourth problem from the shear force bending moment diagram mini-series. And the reason I chose this particular question is because the previous question only looked at distributed loads, whereas this one only has point loads in it. And for the next two problems, I'll probably look at something which has a combination of both, because that's what you usually find in those questions. And once again, this is the kind of problem that you will have, that you might have as a first year engineering student if you're doing some module related to mechanics of solids or structural mechanics or anything like that. So if you want to see anything more like this, or if you have any suggestions, any problems you want to discuss, let me know in the comments. So as usual, I would try to first draw the free body diagram of this, but other than that, this time I'm not going to draw the reaction forces. I'm not even going to, well, I will draw the reaction forces, but I'm not going to calculate the reaction forces, which sounds a bit weird because this is what I say we should do all the time. But in this particular case, we don't have to. You can if you want, and you will end up with two reactions, right? So you'll have a reactive shear force here, and then you also have a bending moment here as well. But the reason we don't do it is because when we try to find that inner bending moment and the inner shear force, we always start from the left and we never actually reach the right hand side. So if we start from the left, normally we have some reaction force here, right? So in this case, the beam is not supported on the left. So there's no point in finding the reactions on the right because we're not going to use them for anything. So I will draw them, I will draw the free body diagram, but other than that, I won't find them. I'll just jump straight into finding the shear force and the bending moment. So here's what we have. We have a beam which has a length of 3 meters, which goes like this, and then it's split in thirds basically. So we have at each 1 meter, we have a point load. So we have a point load acting on the tip. So that's 4 kilonewtons. So again, in this problem, we actually have numbers other than just L's and W's and so on. And this is 6 kilonewtons. And then here we have 8 kilonewtons, like that. And that's it. Those are all the external forces. And then, of course, here we have, I'll use my normal convention of putting the shear force down on the right-hand side. And then we have the bending moment, which is like this. The reaction, I should put like MR and also SR. Okay, so in this case, we have 3 point loads, which means we'll have to do 3 sections. So one here, and then one here. Because remember, point loads are discontinuities in both the shear force and the bending moment graphs. Okay? So my first section is going to be somewhere between the 4 and the 6 kilonewton forces. So I'm going to say that this is 1, and then we have a certain distance x, and then we have the tip load that was 4 kilonewtons, and then on this side we have shear force, and we also have some bending moment. So that's what we're trying to find, right? So sum of forces in the y direction is going to be equal to 0, which means that we have minus 4 because it's down, and we have minus s because it's also down. So the shear force is going to be minus 4 kilonewtons. And then we do the same thing with bending moment. We take moments, let's say about this point, let's call this point P, and we say moments about P, the sum of moments about P is 0, where counterclockwise is positive, so we have M. And then we have the 4 kilonewton, which is producing a counterclockwise moment, so plus 4x equals 0. So the bending moment is minus 4x kilonewton meters. And that's it. That's the first section of the beam. So what we did now was we found the shear force and the bending moment anywhere along this first part. So in other words, we made X between 0 and 1 meter. So for the second part, we're going to consider X between 1 meter and 2 meters. Okay, so in other words, we're gonna take a section here and we're gonna consider this part of the beam and we're gonna do the same thing pretty much. So the free body diagram looks something like this. This is the section of the beam we're considering. And then we have 4 kilonewtons here. We have 6 kilonewtons here. And remember, now we're looking at a length x, where x is between 1 and 2. And then on this side, we have another shear force, and then this is bending moment. Okay, so we know this distance is 1 meter, which means this distance is the remaining, which is x minus 1. So let's first find the shear force. So we have the sum of force in the y direction is equal to 0, where upwards is positive. So we have minus 4 minus 6 minus s equals to 0. So s is equal to minus 10 kilonewtons. And then sum of moments, where counterclockwise is positive, and again, I'll put my point P here. So sum of moments about P is 0, which means that we have M. And then we have two other moments which are both counterclockwise. So we have plus 4 times x. So that's the moment due to the 4 kilonewtons. And then we have plus 6 times x minus 1. So the moment due to the 6 kilonewton force is 6 times the momentum, which is x minus 1. So if we expand this a bit, so we have m plus 4x, and then we have plus 6x minus 6 equals 0. So the moment as a function of x is 6 minus 10x. And that's kilonewton meters. Okay, so the nice thing about solving a problem with point loads is that with only point loads is that you won't get any quadratics. So you only get quadratics if you have distributed loads, but if you don't, you just have some nice first order functions for the bending moment, whereas the shear force is just a constant. So minus 10 or minus 4 in this case. So we sorted that out. So what we essentially did, so in the first part here, we found the shear force and the bending moment for this part. Now we found the shear force and the bending moment for this part. And as you can imagine, now we just have to find the shear force and the bending moment for the final part, for the last meter of the beam. So I'll draw a free body diagram for that, and we shall find the shear force and the bending moment. So that's the beam, which has a length x. So we have 4 kilonewtons. Let's put units, I guess. Then we have 6 kilonewtons. Then we have 8 kilonewtons. And remember, this is not the full length of the beam. This is just some length x. This is 1. This is 1, which means this bit here, this time is going to be x minus 2, right? Because in this case, my x is going to be greater than 2, but less than 3. I can say less than or equal to 3. And then we have the shear force, and then, of course, the bending moment, like this. So let's find the shear force. Sum of force in the y direction is equal to 0. Upwards is positive, so we have minus s, and then minus 4 minus 6 minus 8 is equal to 0. So the shear force will be minus 18 kilonewtons. right? Pretty straightforward. And then we'll do the same thing with the moment. So sum of moments about P, where as usual, my point P is on the cross section. So the sum of moments is 0, which means that we can write M, so the moment, and then we have 3 more moments due to the point loads, and all of them are positive. So we have plus 4 multiplied by, so the moment arm of this is X. Then we have this force, and the moment arm of this is X minus 1. And the moment arm of this is X minus 2. So plus 8 times X minus 2, and this is equal to 0. So we have the moment as a function of X is minus 4X minus 6 times X minus 1 minus X times X minus 8 times X minus 2. So the moment is minus 4X minus 6X plus 6 minus 8X plus 16. So we have the moment will be, so let's see, we have 16 plus 6, so that's 22 minus 18x, and that's kilonewton meters. And that's it. Now we just have to plot everything. So let's first start with the shear force. So let's write it mathematically as a piecewise function, because both shear force and bending moment, they're both piecewise functions. So for the shear force, here's what we have. We have that shear force is equal to minus 4 kilonewtons if x is between 1 and 0. Then the shear force is minus 10 kilonewtons if x is between 1 and 2. And finally, we got it as, I think, minus 18 kilonewtons if x is covering the rest of the beam, which is from 2 to 3. So let's actually plot this. We have the diagram, we have the graph, we have shear force, we have x. So we have, let's see, we have 1 here, this is 1, this is 2, and this is 3. So for the first part, we have the shear force being equal to minus 4. Now, I just realized this is probably not going to be to scale, but it's okay. So this is minus 4. So the shear force just looks like this, a straight line from 0 to just before 1. And then we have minus 10, which is here. So minus 10 happens between 1 and 2, like this. And then I don't really have space for minus 8. I don't have proper space for it, but I'll just do my best to draw it. Just extending this graph slightly. And then we have minus 18 somewhere here. And that is something like that. So that's it. That's the shear force diagram. So that's the shear force diagram. So it's just a bunch of steps, basically. A bunch of constant functions. And let's do the same thing with the bending moment. So we have the bending moment is equal to, and then for the first part of the beam, it was minus 4x. So this was for x between 1 and 0. And I should write the units, but I'll let the units go this time. And then for the second part, we have the moment as 6 minus 10x. So 6 minus 10x, where x is between 2 and 1. And finally, we have 22 minus 18x, where x is between 2 and 3. So this is just going to be a bunch of straight lines joined together, as you can imagine. So let's draw the graph. So we have X here, we have the bending moment here, and then we have the 1, the 2, and the 3. So we have 1, we have 2, and we have 3. Okay, so for the first part, we have the bending moment starting from 0 because you start from the free end of the beam, which is not constrained by anything. So you'll start from the origin, and the bending moment is going to go down to -4 kilonewton meters. So that's going to be -4. Actually, maybe I should put the units here. So X is in meters, and this is in kilonewtons. This is in kilonewton meters, and this is in meters. Right, so for the first part of the beam, we've got this. And then for the second part of the beam, we have, well, let's actually see where where m of, I should take a limit here to be more accurate, but I'll do m of 2 based on this middle function. So that's 6 minus 10 times 2, which is 6 minus 20, which is minus 14 kilonewton meters. Okay, so this is actually going to go even lower, which is to minus 14. So minus 14, again, this is not to scale, but I'll do what I can. So minus 14 is like this, which happens here, which then looks something like this. The slope shouldn't really be the same. The slope should be steeper. So actually, you know what? I'll redraw this on a different page to have more space to do stuff. So let's try this again. So we have this graph, and I should have done the same thing with the shear force, but I'll leave that as it is for now. So that's X measured in meters. That's the bending moment measured in kilonewton meters. Then we have 1, we have 2, and we have 3. Okay, so we have -4 being somewhere here. So the first part of the graph is just a straight line going down from 0 to -4. Then we have -14 as the next point on the y-axis. So -14 is this, which is going to be somewhere. So this is -4, this is -8, 12. I think 14 is somewhere here, pretty much. And that's gonna make the graph look steeper, which is what it should be. Let's try to draw it from here to here. And then finally, for the last part, for the last segment, I'm gonna try to find what is the moment at 3. So at 3, we have 22 minus 18 times 3. So that's 22 minus, this should be 54. So that should be minus 32. Minus 32 kilonewton meters. Yeah, so maybe I should have done the negative part of the graph longer, but I think it's good enough. So I'll draw 32 somewhere, uh, somewhere here. So this is pretty much where minus 32 is, more or less. So minus 32, and that is going to be at 3. And we can draw a straight line like this. Again, the straight line is not really continuing from above because it has a different slope. It's minus 18 instead of minus 10, but yeah, you get the idea. This is the bending moment diagram, like that. This is the shear force diagram, and that's the end of the question.